Avogadro's law kind of is an offshoot of Gay-Lussac's law. So, or his statement up here. So Gay-Lussac's statement, I feel like that's kind of in the wrong way, but he basically said you can combine volumes of gases, right? As long as they're at the same temperature, same pressure, you can just, if I have one gas and another gas, I can just add them up and that would be double the volume or whatever. So Avogadro's law is from Amadeo Avogadro. So this is one of his important things, in addition to Avogadro's number, obviously. But his big contribution was with gases, which is where Avogadro's law came from, or Avogadro's number came from. He was contributing with gases because he found out that the volume of a gas at a certain temperature and pressure is directly proportional to the quantity of gas you have. So he said that if you increase your amount of gas, so if we increase moles of gas, then obviously my volume should go up. There's more gas, there should be more space taken up, right? And vice versa. So he said those were directly proportional as long as you're at constant temperature and pressure. So if I have 4 moles of gas, I can actually combine those volumes together as long as they're all at the same temperature and pressure or whatever. So Avogadro's hypothesis says that equal volumes of gases under the same conditions have equal numbers of molecules. That's really what he said. So remember that it's really equal numbers of moles, right? But we're going to say molecules because we know that 1 mole is equal to 6.02 times 10 to the 23rd atoms or molecules, right? So since we already know Avogadro's number is like a nicer way, mole is a nicer way of writing Avogadro's number, they're kind of go hand in hand. So if we have volume, equal volumes of gases are going to have the same number of moles, then they would have the same number of molecules as well. Like, obviously, it should make sense. So here's just kind of another picture, a depiction of Avogadro's law. Again, it's a direct relationship. So when we look at that relationship, we see that as my moles, we increase my moles, what we just said earlier should happen is we see that the volume of the container is going to increase. So there's more gas in there. That the volume has to expand to make up the difference for that. And it doesn't matter what kind of gas it is because there's large spaces amongst the gas molecules. So it doesn't matter if it's in this, that's what this picture on the right is showing. If it's N2 or H2 or argon or CH4, if they are at the same conditions of temperature and pressure, then the volumes, if they have equal volumes, in this case it's showing pictures of the balloons being equal volumes, then they must be equal moles or quantity, right? And it says this below it, these balloons each hold 1 liter of gas at 25 degrees Celsius and 1 atm. So then each balloon has 0.041 moles of gas, or 2.5 times 10 to the 22nd gas molecules. So it's really easy to figure that out. So if we wanted to know how many particles were in each balloon, right, we could easily figure that out because how many particles are in each balloon? Well, the conditions of the balloon are the same, right? So the conditions are the same. So if the conditions are the same, then what would we do? They have 0.041 moles each, right? And it's just generic moles of gas. So we can do a quick conversion, and that's how they got that number. 1 mole of gas is equivalent to 6.02 times 10 to the 23rd. I'm going to say particles of gas because it's atoms or molecules. And when we multiply those together, we should get 2.5 times 10 to the 22nd gas molecules. So each of those balloons has the same quantity of gas because they're at the same temperature and pressure, and they have the same volumes. So as long as they have the same volumes, we know that's going to be the case. So that's essentially all of our variables. So if we go over to the next, there is an actual problem for Avogadro's law, right? So exercise 6 says, suppose we have 12.2 liter sample that contains 0.5 moles of oxygen gas at a pressure of 1 atm and a temperature of 25 degrees Celsius. If all of this oxygen were converted to ozone at the same temperature and pressure, what would be the volume of the ozone? Okay, so this one's a little bit more complicated. It makes us think about a little bit about reactions. We haven't spent a lot of time on them yet, but we will. But let's think about, this is a very easy one. We're taking O2 gas and we're converting it to O3 gas. And hopefully you remember from first year chemistry that these don't match up in law of conservation of mass. So we would need coefficients to make that match up. So I'm going to need 3 O2s for every 2 ozones that I make, right? So pretty easy. So that is my mole ratio right there. So if I know the moles of one, I can find the moles of the other. That's the only reason you need that. So when we look at this, it says, suppose we have 12.2 liters. So there's our volume. And we have this many moles of O2, right? So there's my N. And it says at a pressure of 1 atm and a temperature of 25. If all the ozone is converted to, or the oxygen is converted to ozone at the same temperature and pressure. So notice same temperature and pressure. So this is just a direct relationship. What would be the volume of the ozone? So we want the new volume 2, right? And so these are directly related as well. So my volume 1 over N1 equals volume 2 over N2. That's the relationship. It's the same one we just did with volume and temperature with Charles' law. We're just switching out, keeping temperature constant and changing the amount of gas. So we can plug into that. But before we can do that, we have to do a conversion to figure out how many moles of ozone I have, because I want that other volume. So if I have 0.50 moles of O2, so we got to do a little quick conversion here. Moles of one, we can find moles of the other. So it's using a little stoichiometry, little preface. We're going to do this soon. So moles of O2 are up. So 3 moles of O2 come down, and 2 moles of ozone are going to go up. So we're going to basically take 0.5 times 2, which is 1, divide that by 3, and we should get 0.33 moles of ozone, right? So logically, okay. So it should make sense because we have less ozone. So we should have a lower quantity moles because we converted most of the oxygen into ozone. So we have less moles of ozone at the end. So when we go to plug in, I'm going to switch colors so you can see it a little better. We go to plug in, my initial volume is 12.2 liters, right? And that's for the 0.50 moles of O2. But we converted that moles of O2 to ozone, so now it's something different. So some of those oxygens have been consumed. So we should see a decrease in the volume because we have less moles of gas when this happens. So the new volume 2 over 0.33 moles of ozone, when I do the math, like cross multiply divide, my new volume, obviously we talked about, should be less than what we started with. So we started with 12.2. When you do the math on this, you should get 8.1 liters. Hopefully you did your algebra right. Which should make sense because if you decrease the moles of gas within the container, then you should see the volume of the container should get smaller as long as obviously it's expandable.